Good evening. This series of conferences coordinated by Professor Anna Chúcaro and sponsored by the BBVA Foundation are entitled The Science of the Cosmos and the Science from the Cosmos. This title tries to emphasize the fact that the role of the universe in the science are really twofold. In the first place, of course, knowing the structure and evolution of the universe is a really very ambitious project. However, in addition, studying the universe can provide us with fundamental clues to understand physical laws that actually are in extreme conditions not reachable in the Earth. The talk, the lecture that Professor Cronin is going to give us today is a well example of that. Actually, he will point out this double character of the science of the universe. Nearly 1 century ago, Victor has discovered cosmic rays. In fact, this discovery was also the birth of particle physics. Professor James Cronin, as a graduate student in the University of Chicago, was really attracted by particle physics in those days. A few years later, after finishing his PhD thesis, he moved to Brookhaven National Laboratory, where a lot of exciting and interesting new results were taking place. For instance, violation of parity, the discovery of the long K meson, and so on. A few years later, in 1964, he carried out a very historical experiment, now as a faculty of the University of Princeton, and the result of this historical experiment was the conclusion was the violation, the conclusion was the violation of the CP symmetry. This is actually a very important and relevant result which has changed our view of also of nature. Actually, in a few words, the violation of CP the CP symmetry would predict that in a microscopic system, we replace particles by the corresponding antiparticles. The process is equivalent to the image mirror of the mirror image of the original process. So, actually, this has very important implications in our understanding of nature, because it means that it implies that nature, in a certain way, has a preference of matter against antimatter, and perhaps this is the reason why matter exists at all, and we, that of course we are made of matter, exist at all. This important, very important result was rewarded with the Nobel Prize of Physics in 1980, shared with Balfitch. But I would like to stress that Professor Cronin is an experimental physicist, and before achieving such interesting and such fundamental results, he had to work very hard in developing and improving some experimental tools. For instance, the spark chamber, he was much involved in the development of the spark chamber, and actually it became in those days a fundamental tool for registering the tracking of charged particles in experiments in accelerators. In 1971, James Cronin moved now as a full professor to the University of Chicago, where continued research in particle physics using a new facility, that is the new accelerator at Fermilab, which was close to the University of Chicago. In the 80s, he was attracted by the problem of the origin of high-energy cosmic rays, and actually, in these days, he developed and improved the idea of using a large array of detectors to register the particle shower initiated by a cosmic ray in the atmosphere. This result was the experiment CASA, which was a really very good result carried out in the United States. And I can tell how well CASA worked, because it happened that in those days I was working in the European competitor Hydra, and we all know that CASA was extremely well designed. You got extremely good results out of this array. A decade later, I would say again, another step forward. In 1992, James Cronin, together with Alan Watson of the University of Leeds, proposed the construction of a huge array for the detection or for the observation of the so-called ultra-high energy cosmic rays. This idea has given rise to the Pierre Observatory, which is operatively taking data since several years ago. And now this observatory is providing us with the best, with the most accurate results on these cosmic rays of such a high energy, actually microscopic energy, just concentrated in single particles. The origin of these particles and also the physics underlying the generation of such a high energy in cosmic accelerators is actually unknown. Nowadays, Professor Cronin, as emeritus spokesperson of the OJ collaboration, continues his scientific activity, attending most of the meetings of the observatory. And I would like just to tell you that the observatory is located in Argentina, in the so-called Pampa Amarilla, at about 450 kilometers south of the city of Mendoza, without any operative, or at least I would say reliable, airport in between. It means that the trip to the observatory is really very long and tired, but still Professor Cronin used to come very often. Just to finish, I would like to say that we, all the members of the scientific community of particle and cosmic ray physics, are really indebted to Jim Cronin for his contributions to these fields, which are leading us through new and exciting discoveries. Therefore, it's truly a pleasure and an honor for me to present Professor James Cronin from the University of Chicago, which is going to give a lecture on cosmic rays, the history and present research, an exciting field in between astrophysics and particle physics. Professor Cronin.
Thank you, Fernando, for the unbelievable introduction. I don't think I can really live up to the reputation you assigned to me. And I'm very thankful to the foundation BVA. I probably have it wrong, but Professor Prado will excuse me, I'm sure. And in fact, I see it's wrong in even in my little introduction there. But what I'm going to talk about is the history of cosmic rays. It's a discovery in science which in some sense was completely serendipitous. It wasn't expected. And the phenomena that were observed more than almost 100 years ago were not really understood until the mid-1950s in 1953. So I'm going to go through and give a few vignettes of this history, and then I will talk just very, very briefly about some modern experiments that in some sense derive their origin from cosmic rays. Now, what are cosmic rays? I'm sure many of you do know that, but let's just go through it. It's radiation from outer space. It's from the sun, our galaxy, or even outside our galaxy, depending on the energy. The higher the energy, the more remote the origin of the cosmic rays are to the extent we know it. They are atomic nuclei. It's not really radiation, but it turned out that they are atomic nuclei which run from protons to iron, iron being the most stable nucleus. And they span a range of X-ray energies, a few kilovolts, to 10 to the 20th electron volts. 10 to the 20th electron volts is 16 joules, which is a macroscopic energy. So we're dealing with some sort of systems that can accelerate or produce particles particles which are microscopic but have macroscopic energies. And the low energy ones of these enter our atmosphere and form in the northern and southern hemispheres the aurora borealis. The annual exposure, this is radiation we cannot avoid. The annual exposure is the order of a few dental x-rays. And this is about 10% of the allowed exposure for atomic workers. And in fact, in this room right now, about 200 muons, these are debris of the cosmic rays, are passing through each square meter per second right here. So all of you are being penetrated by cosmic rays as we sit here, and there's no way to avoid it. Now, the question, one important scientific question at the end of the 19th century, does air ionize spontaneously? And what this means, I can explain a little bit. I think many of you have, in your school career or something, have seen a gold leaf electroscope. This is an example that if you charge up this, there's a gold leaf here, and like charges repel, so the leaf extends out when you charge it up. But this device will on its own discharge. It doesn't keep its charge. But experiments had been done where the device is isolated, put in a vacuum, and then it did not discharge. So before, as I will say, before the discovery of radioactivity, this was a fascinating scientific problem. Does air itself fully ionize? Now, by ionization, I mean that something takes an atom and strips an electron or a couple electrons off of it, so you're left with free electron and free atomic nucleus. This, if there are potentials, this can make current, and so a current will flow just automatically. And so, as I hinted before, the answer at the beginning of the 20th century is that thought to be ionizing radiation from the ground following the discovery of radioactivity by Becquerel, and radioactivity in some sense was everywhere. And the question was really a quantitative one. Could we just say, yes, this is background, let's not worry about it? And most physicists, in fact, took that point of view. I want to study radioactivity. I don't care if there's a little background. But there was a small subset which included some fairly significant physicists like C.T.R. Wilson, who invented the cloud chamber, a classic pair, Elster and Geisel, Rutherford, his colleague Eve, Schrödinger, and a sort of unknown physicist, Italian physicist, who was more like a meteorologist named Pacini. And they all asked the question, can we explain the discharge of these electroscopes using the radiation on the ground? And the way that was finally conceived, if it really is radiation on the ground, then if I take my detector and take it far from the ground, climb the Eiffel Tower is one example, go up in the balloon is another example, then the radiation should decrease. And one beautiful detector, and one of the first really nice experiments was done by a Society of Jesus priest named Theodore Wolff from Holland, and he built an electroscope, which is really a lovely design, was used by many, many people, where one has stretched wires, and when you charge it up, the repulsion of the like charges drives the wires apart, and how far they are apart really tells you how much charge is contained. And so this was the kind of device that Wolff invented. And then he traveled from Valkenburg, which is in Holland, to Paris. And then at the bottom, and now we're measuring, and this will be true for a number of slides I'll show, you measure the ionization in the number of ion pairs per cubic centimeter per second produced. And so when he went to Paris, there was something like 17.5. climbed up the top of the Eiffel Tower, made many measurements, went back to the ground, and then back home again. And the result was that at the bottom of the tower it was 18, and at the top of the tower is 15.7. It's very hard to estimate what the error is. In these days, people would publish numbers and rarely talk about what was a possible error. You can get some idea about the errors from the fluctuation of these numbers. But in any case, it's maybe a slight indication that the radiation went down. But in fact, it didn't go down nearly enough going up the 300 meters or so to the top of the Eiffel Tower. Now, a more effective way to take a detector away from the ground was in balloons. And this was done by a number of people. There was a Swiss named Gockel, but then it was Victor Hess who's shown, I think, before the launch of one of his flights. He took many flights, looking very dapper, and went up in a balloon. And here is a picture of one of the balloon launches from Vienna. And these balloons were usually filled with illuminating gas. But in order to get enough lift, finally they had to be filled with hydrogen, which is a bit dangerous. And this Hess took 7 flights, and in 1912 he got to the highest level, which is a little over 4,000 meters. And these are some of his readings. The one that is was some of the devices were sealed and other devices were open in the air and had to be corrected. And in the next slide, I just type out what he actually observed. There's the height in meters from 0 to 3,500, and the ionization going from 19.6 ions per cubic centimeter per second up to 35.2, essentially a factor of 2. And this was the first evidence that instead of the radiation going away, the radiation increased as one went up in the atmosphere. And the conclusion, although it was debated over many, many years, was that radiation is coming into the atmosphere from outer space. And what it was, one had no idea. At that time, the kind of radioactive products were either electrons, alpha particles, or gamma rays. Gamma rays were the only radiation that was really penetrating, so it was automatically assumed that these were gamma rays. This is a picture of Victor Hess, who, after a long, long time in disputes, of which I'll cover a few, received the Nobel Prize in 1936, along with Anderson, who discovered in the cosmic rays the first new particle, which was the positron. Now, shortly after Hess's flight, a Professor Werner Kohlhoester from Berlin got involved, and he went much higher than Hess. And this is a copy of his paper published in 1914. He had taken some flights, and this is a flight that went up to about 9,000 kilometers. And he had to fill the balloon with hydrogen, and he had to have oxygen to breathe so he did not pass out. And his measurements are really quite dramatic. This is now the ionization. You see it at the ground, it's somewhat less than 20. But as he went up in altitude to 9,000 meters, the rate just increased essentially exponentially. So it's almost 10 times more radiation at 9,000 meters than you have on the ground. And this was further evidence backing up Hess's original work. And it's hard, I would love, the papers of Kohlhoester are lost. They were lost during the war, as far as they don't exist. But it would be so interesting to get his impression of what it was to take such a daring flight to such heights for a scientific purpose. You know, it is amazing what people will do when they're possessed to measure something in science. They'll take big, big chances. Now, you notice that Kohlhoester's work was published in 1914. In August of 1914, the Archduke Francis Ferdinand was assassinated in Sarajevo, and the long, bloody war began, the First World War, so all science stopped. After the war, cosmic ray research resumed, and one of the principal characters is an American, Robert Millikan, who many students may know from the Millikan oil drop experiment that they had to suffer to do, and also he measured the photoelectric effect. A very great physicist, but a very opinionated physicist. And he believed that the work of Hess was really not all that significant, and he began his own research in cosmic rays, which had some ups and downs. But finally, Millikan believed that he discovered cosmic rays, or he had that sense, and Hess was not very happy about that. So in one of Hess's papers in 1926, wrote in German that he's just extremely unhappy with Millikan. My German is not particularly good, so I translated it. And this is a rough translation that Hess is writing in this paper. As concerns the publication of Millikan cited above, I would like to remark that he tells a story of the discovery of cosmic rays that could easily be misunderstood. The recent determination by Millikan and his colleagues of the highly penetrating power of cosmic rays has been an occasion for American scientific journals such as Science and Scientific Monthly to introduce the term Millikan rays. Millikan's work is only confirmation and extension of the results obtained by Gockel and myself and by Kohlhoester from 1910 to 1930 using balloon-borne measurements of the rays. To refuse to acknowledge our work is an error and unjustified. But in some sense, Millikan had the last word because he went on many lecture tours, and in a lecture he gave at Leeds University, he's quoted as saying, talking about his work, all this constitutes pretty unambiguous evidence that the high altitude rays do not originate in our atmosphere, very certainly not in the lower 9/10 of it, and justifies the designation cosmic rays. So cosmic rays as a term was defined by Millikan. It had been known in the German as Hohenstrahlung, which made good sense as well. We still have Bremsstrahlung, but here we have cosmic rays. And the word ray is misleading because you do think of radiation like gamma rays, and he was convinced totally that this radiation was gamma rays. And he had his own ideas. This is a paper published by Millikan and Cameron, and what his idea was that Aston had measured with mass spectrometer the mass of nuclei, and nuclei, as you went from hydrogen to helium, eventually to iron, became more and more bound. So there was the binding energy. And Millikan had the idea, if all of a sudden, say to make an iron nucleus, all the positive charged particles, all the negative charged particles far out in space came together all at once, the result could be a gamma ray of fairly significant energy. And therefore, I don't know that he made this term, but it was attributed to him. These are the birth cries of atoms. We'll get back to this soon. But very clever idea, but really had very little solid experimental basis. Now, then this raised the question, what are these cosmic rays? Can they be something other than gamma rays? And so the development of new instruments, particularly the Geiger counter, which would detect charged particles, was taken on by Botha, who built a way of measuring electronically the coincidence between two particle detectors or Geiger counters. Let's look at the next slide. This is a translation of famous paper of Kohlhoester and Botha in 1929. And they put together this piece of apparatus where there were two Geiger counters separated by about 4 centimeters of a gold absorber and then shielded all the way around. And what they found was that the rate of coincidences between these two counters, that is being triggered essentially at the same time as a particle, as the ray, which turns out then by this experiment, turns out to be a charged particle. And the conclusion is, at least at the surface of the Earth, the radiation is corpuscular. It's not gamma rays, but it is charged particles. And this is a very, very important experiment. And then challenged the idea that the cosmic rays were in fact rays or gamma rays. And about this time, some very important people became interested in the cosmic radiation, particularly Bruno Rossi here, who's shown in a meeting in Rome discussing some problems of cosmic rays with Enrico Fermi. Enrico Fermi has followed, but never did exact work on cosmic rays, but followed the field closely ever since this meeting. But now Rossi, in a memoir, writes the following, because Rossi was really the physicist who put cosmic rays and the study of it on a really important scientific basis. And this is interesting to me to write. He says, for me, the turning point in the search came in the fall of 1929 with appearance in Zeitschrift für Physik of the historical paper Das Wesen der Hohenstrahlung. That's the nature of Hohenstrahlung by Botha and Kohlhoester. That's the slide I just showed before. And this is Rossi now. Until then, I had not been particularly interested in the phenomena of the Hohenstrahlung or cosmic radiation, using the suggestive expression introduced by Robert Millikan. I had not thought it would offer to me at least a profitable field of research. In 1929, Rossi had just gotten his PhD in physics from the University at Bologna. I had not been seduced by Millikan's well-publicized theory maintaining that cosmic rays were the birth cry of atoms in cosmic space, being born in the form of gamma rays when hydrogen atoms fused to form heavier elements. To my skeptical mind, this was a romantic idea lacking sound experimental support. And if there's anything about Rossi, he insisted on making experiments that were solid and well carried out. On the other hand, I had accepted uncritically the prevailing view that primary cosmic rays were high-energy gamma rays. Therefore, I read with particularly keen interest the paper by Botha and Kohlhoester relating the first attempt to submit this assumption to a direct test. That is, the Botha and Kohlhoester experiment showed that at sea level at least, most of the cosmic rays were charged particles. Now, Rossi did many, many experiments, but there's only one I'll point out, which is kind of dramatic. That Rossi, first of all, was great in making electronic circuits. So he built coincidence circuits that would register coincidence between 1, 2, and 3 counters simultaneously, meaning that this counter, and this counter, if there is a coincidence, trigger at the same time. And what he made a pile of 1 meter of lead like this and showed that at least 50% of the radiation at sea level was charged particles and would penetrate a meter of lead. Now, this is a complete surprise. Nobody had any idea what kind of particle could do that. And this was just one step in the final establishment of what the cosmic rays finally were. Then I said that this Botha and Kohlhoester and the Rossi showed that there are charged particles for the most part, on the ground. But what about the primary cosmic rays that are coming in from outside? What is their, are they charged particles, or maybe they're gamma rays which then make charged particles in the atmosphere? So a very important idea was exploited perhaps first by Arthur Compton, that using the Earth's magnetic field, that one should see a modulation in the intensity of cosmic rays as a function of magnetic latitude, which is basically latitude because the magnetic pole is close to the real pole. And so studies were made by him and reported, a geographic study of cosmic rays where he organized with many, many colleagues all over the world, stations. But let's back up a minute. This is Compton, a very handsome man, but what he built was a standard detector, which was could be built and replicated many, many times, and standard ways of radioactive sources to calibrate it. This is a essential electrometer ionization chamber filled with 50 atmospheres of a noble gas. So he arranged to have these built and distributed to colleagues all over the world in these black spots here to do a survey of the intensity of cosmic rays with a common apparatus as a function of particularly latitude, but also, of course, longitude. And this is geomagnetic equator, which is pretty close to the real equator. And then what was found is a variation of the cosmic ray intensity with the geomagnetic latitude. And the intensity is lower at the geomagnetic equator because there's stronger magnetic fields which deflect the cosmic rays, being, if they're charged, from hitting the ground. And these are measurements at different altitudes as a function of latitude, and one can see when you got close to magnetic pole, the rate of the cosmic rays was higher than at the equator. Now this is extremely important because it demonstrates the Earth's magnetic field extends way beyond the atmosphere, so that the cosmic rays that were coming to the Earth were in large part charged particles. This contradicted the idea of Millikan that they were gamma rays, because it was shown they were charged on the surface, but maybe they were not charged when they came into the Earth's atmosphere. So this is extremely important. But the study of the latitude variation of cosmic rays became very popular, and a number of people, sorry, I'm getting hit, I'm sorry. Let's finish with Millikan now. I'm getting ahead of myself a little bit. In fact, the lecture's a little badly organized, I realize. But in any case, there was a meeting of the American Association for the Advancement of Science on New Year's Eve, 1932, in the depth of the Great Depression, where Millikan and Compton both attended. And here you see the headline written by William Lawrence, a science journalist who later covered the whole atomic bomb project. Millikan retorts hotly to Compton in Cosmic Ray Clash. The debate of rival theories brings drama to session of nation scientists, their data at variance. New findings of his ex-pupil, Compton, lead to thrust by Millikan of less cautious work. Now let's look at a little bit of this article. In an atmosphere surcharged with drama, in which the human element was by no means lacking, the two protagonists presented their views with the vehemence and fervor of those theoretical debates of bygone days when learned men clashed over the number of angels that could dance on the point of a needle. Dr. Millikan particularly sprinkled his talk with remarks directly aimed at his antagonist's scientific acumen. There was obvious coolness between the two men when they met after the debate was over. But this ended the question of what the nature of the cosmic rays were. Not what they were, but they were charged particles coming in from outside the atmosphere. And as I was saying, it was very popular to study this magnetic latitude effect. And I use this to introduce two new characters in this history of cosmic rays. The French physicists Leprince-Ronguet and Pierre Auger in 1934 boarded a ship in Le Havre and sailed all the way to Buenos Aires, crossing the magnetic equator, measuring the rate of cosmic rays. And this is the only thing I have in Spanish, which is an article I found in the archives of Leprince-Ronguet and Pierre Auger arriving in Buenos Aires. And they, in fact, did measure this. I had the opportunity to interview Leprince-Ronguet in his 99th year, and he remembered very well this voyage. And he told me that Auger was smart, sort of theoretical, but he couldn't change the batteries in the apparatus. And these two gentlemen came from aristocratic background and a very common background, the two. Leprince-Ronguet was an engineer who oozed into physics, but quite dramatically. So we'll come back to him in a moment. Now, Pierre Auger played a very important role in the development of cosmic rays. And he also was an artist, and this is a self-portrait of Auger that he drew. And here he is. He was a very important French physicist who did some atomic physics first, and people may have heard the Auger effect, which is an emission of electron from atoms. And then most of his life he spent studying cosmic rays. And he did an experiment in 1938, in which was a very simple experiment. Again, we have Geiger counters as Bode and Kohlholster had and Rossi had, and they were arranged in this kind of arrangement. Two counters like this, one on top of the other, and a third counter that could be varied in distance between two. So you think of this defining one cosmic ray particle, and then look in coincidence if there's another cosmic ray particle. And down here are the data in counts per hour. I've reprinted it here. So this is in the laboratory in Paris. At 2 meters separation, there were 1.7 counts per hour, a very low rate, and it took a lot of care to be sure that that was a real rate and not just accidental coincidences. At 5, the rate went down a little bit, but at 20 meters, it was still within a factor of 2 of the original rate. This meant that with 20 meters of separation, a particle here and a particle there had a common origin. And by that time, there was enough understanding of at least electromagnetic showers in 1938 that he could, on the back of an envelope, which I'm not going to do here, estimate that these cosmic rays maybe had an energy of something like 10 to the 13 electron volts. But in order to follow this up, he took his apparatus to the Alps, and again, being a cartoonist, he drew this lovely picture of traveling the Alps with his trailer, and this is the top, and this is the bottom. Don't turn upside down. Bern, 321 kilometers. The car is broken down, and here he or his colleague is underneath trying to repair it. This is, the sense of humor of this fellow was quite extraordinary. And then these are the combination of his measurements in Paris and in the Alps. And here in Paris, this is a dashed line, by about 20 meters, the rate, this is the rate, or relative rate. It's in a logarithmic scale, but that doesn't matter. But then going to the Alps, one found that one still had coincidences a common source of two particles in the cosmic radiation that were separated by 300 meters. Then again, when one did the calculation, he estimated that these are cosmic rays of 10 to the 15 electron volts. Now that's huge energy. Artificial radioactivity and things like that had maybe 10 to the 6 electron volts. 1 MeV, 10 MeV. So here nature, he demonstrated that nature is producing the incoming radiation, which is, at least some of it is as much as 10 to the 15th electron volts. And this was quite sensational at the time because there was no artificial way of getting energy, anything close to that. And he traveled to Chicago. There was a cosmic ray conference in July 1939 at Chicago. And what I want to emphasize here is that cosmic rays at the time, in 1939, was one of the hottest subjects in physics, just judged by who's there. Here's Heisenberg, here's Bode, here's Beta, here's Compton, Teller is, let's see, he's here somewhere. This is Oppenheimer, and here is Pierre Auger right here. These are, look, you can't see very well, but Pierre Auger is probably the best dressed guy. But note that everybody is well dressed in those days. No blue jeans and sweatshirts and things like that. You would never get a group of physicists who look so good. And this was a very important conference and marked, again, the end of research, because in September the 1st, the Nazis invaded Poland and the Second World War began. But I just stress that everybody was interested in the nature and origin of cosmic rays. And this is Pierre Auger gave on the behalf of his group a talk in which the conclusion was one of the consequences of the extension of the energy spectrum of cosmic rays up to 10 to the 15th eV is that it is actually impossible to imagine a single process able to give a particle such an energy. It seems much more likely that the charged particles, which constitute the primary cosmic radiation, acquire their energy along electric fields of very great extension. It's not clear that is the way, but it was clear that it was a great mystery how objects in nature could accelerate cosmic rays to such high energies, and we will come back to that. Auger, when France was invaded, went first to Vichy, France, and then traveled by boat to the United States and spent 1 year at my university, University of Chicago, and here he is organizing a balloon-borne piece of apparatus which had Geiger counters here and Geiger counters here, so in some sense measuring the coincidence rate between two well-separated counters as a function of altitude. This was taking place on the athletic field, and over here somewhere during 42, Fermi was building the first chain reaction, which happened on December 2nd, 1942. But Auger knew nothing of that, and in fact, he would like to have worked on the project, but he was considered unreliable, and he went to Canada and then eventually back to France, working in operations research for the Free French. Enrico Fermi, in December of 48, this is wrong. Fermi is right, this is 1948 if you can read it, developed a theory of the acceleration of cosmic rays, which is known as Fermi acceleration. And his idea was that they're moving magnetic clouds, and when a charged particle hits this cloud, it gets randomized in here and gets ejected again. So it's like an elastic collision of a particle with a magnetic cloud. And if it hits another one, there is, of course, a loss and a gain, whether you're moving away or moving towards it. But in any case, there's a net gain of the mass of the particle times the square of the velocity of the cloud. He does this non-relativistically and then just assumes automatically it's the energy of the particle times the velocity of the cloud measured in units of c. This is very typical of Fermi. And he worked on this over Christmas and submitted a paper on the origin of cosmic radiation in January 39. Just a few weeks of work was submitted. And note, it was published in April 15th, just about 3 months. That's unheard of now, to submit a paper and have it published so quickly, unless it's a really great discovery. And the other thing that's interesting to point out, that the last sentence here, he points out the problem with this theory. The chief difficulty is that it fails to explain in a straightforward way the heavy nuclei observed in the primary radiation. How unusual it is for somebody in the abstract of their paper to say what's still wrong with it. And what was wrong is that the heavy nuclei would lose energy by radiation faster than they could be accelerated by the collisions with the magnetic clouds. Now, in 1953, after the war, a very important conference was organized by Laprence-Ronguet, and it took place in the Pyrenees at a town called Bagnères de Bigorre. And Laprence organized this conference. It was a typical cosmic ray conference, but he said, let us spend only time talking about new unstable particles that have been discovered in the cosmic rays. It was organized with Blackett, and this is Laprence-Ronguet here, and this is Rossi. You can't resolve that, but those three gentlemen played a very important part in this conference. And as I'll say, this conference is a watershed in which the discussion of the particles, heavy unstable particles, which had already been pi mesons and mu mesons discovered, but then particles called eventually the lambda particle, which are a proton and a pion, and these two very interesting so-called now K mesons, but they're called tau particle at that time, decayed to 3 pi's, and then a V2, which came to be known theta particle, decayed to pi plus, pi minus. Now, what was remarkable and brought out very clearly in this conference, that the mass of these two particles was essentially the same to within a few percent. And Rossi was given the task of summarizing the conference. 6 whole days discussing only these heavy unstable particles. Every other aspect of the cosmic rays was put off. Organizing the conference is extremely interesting to read in archives about it, because there were so many people working on other aspects of cosmic rays. They were very unhappy, but the beauty of concentrating all the experts in the world on the particle physics aspects of cosmic rays paid off, because it was everybody's ideas and were much more clearly expressed. And I include this paragraph, which was stated by Rossi, who had the job in one afternoon to completely summarize the whole conference. And he writes, before concluding my remarks here, having gone over the whole conference, there's one point which I would like to make, which was made already in the course of the conference. It is the very close similarity between the masses of 2 of the best established particles. I mean, the charged tau particle with a mass of 970 electron masses, and the theta 0 particle. The tau went to 3 pi's, the theta 0 went to 2 pi's, particle with a mass of 971. This looks hardly like an accident. And on the other hand, it is very difficult to see how the theta 0 particle could be the neutral counterpart of the tau particle. This is the first indication of an introduction of a puzzle which was known for many years as the tau theta puzzle, which eventually became so evident that it led Li and Yang to predict the possibility that, or contemplate the possibility that parity violation, as left-right symmetry was violated in the interactions which govern these particles, the so-called weak interactions. Now, what I want to say at this point is that after this conference, it was very clear what was going on in a fundamental way with these particles, all found in cosmic rays. It was such that it enabled Abraham Pais to write about associated production. I know these are all technical things, but I just want to stress that, and Gell-Mann to make a scheme of organization of these particles, which he called strange, which was completely correct and predicted many new particles, all based on cosmic rays. You will find now youngsters who work with accelerators and never realize how much was done with the cosmic radiation. And 20 years later, the Prince Ranguet is reminiscing about this conference, which he loved. He forced it to be concentrated. And he writes, the Congress at Bagnères de Bigorre, I was saying, sounded the death knell for cosmic rays. And it was Powell himself who made the closing talk, said, gentlemen, now we are invaded, we are submerged, the accelerators are coming. And this conference did mark the transition, at least for subatomic physics, as we might call this, from cosmic rays to accelerators. At Brookhaven, a 3 GeV machine was just beginning to operate. It could make K-mesons, it could make lambdas, and take over and study in detail all these discoveries which were coming from cosmic rays. And you can see also in the 40 years or so since the discovery of the cosmic rays that one finally understood basically what they were, which was very high energy protons for the most part entering the atmosphere, making all these secondary particles in the atmosphere. So that cosmic rays really led to the birth of what one might call subatomic physics. So in 1953, after Bagnères de Bigorre, subatomic physics moved essentially to the accelerators, not exactly at that time, but gradually moved there. And cosmic rays, because the beginning of space satellites and so forth, moved to space. But there's a little asterisk there that says, but on the surface for the highest energies, because the highest energy cosmic rays were very rare, and you could never build a satellite big enough to detect any of them. So there are sort of three lines that develop out of Bagnères de Bigorre, which are accelerator physics, subatomic physics, and cosmic rays both on the ground and in space. Now, subatomic physics today, well, it can be encapsulated in this picture, which is a Large Hadron Collider, which has been successfully running at CERN now for a year, and demonstrates the progress in the field is huge, so many discoveries made, but one has to build a giant apparatus to further the study, and it involves huge teams of physics. And I know in Spain there are many teams working on these big detectors. Now, what about very high energy cosmic rays today? Auger made the discovery of extremely high energy cosmic rays. Now, since this is my specialty, I'm going to have a few preliminaries just to sort of be able to finish my remarks. And when a very high energy cosmic ray enters the atmosphere, by the way, this is a figure often used. It was produced by Enrique Sas at Santiago de Compostela, and it's used again and again and again. A single proton will enter the atmosphere, and in the first interaction in the atmosphere, it will perhaps produce 1,000 particles if it's a very high energy. And each of those in their interaction will produce 100. And then each of those in their interaction will produce 10 and so forth. So a cascade of a single particle entering the upper atmosphere multiplies into something like 10 to the 10th. There's 10 billion particles in the atmosphere, and most of those then hit the Earth. So you can detect these, what we call showers of particles, by particle detectors on the ground. But there's another way which exploits the fact that charged particles passing through nitrogen produce near ultraviolet radiation between 300 and 400 nanometers. It's not very much. It's maybe 4 such photons per meter. However, if you have 10 to the 10th particles, that's a lot of light, and many kilometers away, it can be observed by sensitive telescopes with sensitive detectors. And so after the war, Rossi and his team began to study the cosmic rays by building an array of detectors so the shower of the many particles would hit. And these were beginning to be quite large, a scale of 100 meters, so it's about 500 meters across. And they were able to show that there is cosmic radiation that is greater than 10 to the 18th eV. Now, these were built with new detectors, which were scintillation counters, and they were able to measure timing quite accurately. So by relative timing between 5 and 3 and 2, you could infer what the direction of the particle was, or the shower that was being detected. And they were sure that you would find that all of these showers would lie in the galactic plane, because that's all the material is in the galactic plane. They found no such asymmetry whatsoever. This continued, and also in the Soviet Union, here is a famous Russian physicist, Tsetsepin, who is doing his hard work laying out cables for one of these cosmic ray detectors in the Pamir Mountains. He wasn't content just to sit at his desk, but he did real work. And then working out of doors, there are all kinds of new hazards. And here is John Lindsley, who was sent to New Mexico to build a larger array. And this is one of his detectors. Here's the roof, and it's insulated by straw. And he's being sure that there's not a rattlesnake, a poisonous rattlesnake, hiding in the straw before he services the detector. So you're dealing not with just antiseptic counting rooms at accelerators, but in this kind of work, you're dealing with the entire out of doors. And Lindsley's work was paid off by discovering a single event in 1963, which was essentially, it hit here, and he had counters now spread out on a kilometer scale, and the energy of this particular shower, one and only one that he found, this energy was of the order of 10 to the 20th electron volt. So it seemed that there was no end to the cosmic ray spectrum. So what do you have to do? Well, this is now high energy cosmic ray today on the ground, and among many things that were built over the time, this is essentially the last, maybe not last, but the biggest detector ever built, and Professor Arcaro is involved in this, 16 countries, built in Argentina. I'm not going to go to all the details, but it is a series of essentially 1,600 detectors spread out of over 3,000 square kilometers. So this then in some sense is comparable in the scale to what we had to do in particle physics to continue to make progress if you were interested in the highest energy cosmic rays. Now let's just take one example. I mean, I don't have time to give a lecture on the results of this experiment. I'd be happy to do so in a few years if I were invited back to this foundation. But just before the large array in Argentina began, there were two experiments, one which used the ground technique, the Japanese experiment, and another one which used the technique seeing the nitrogen fluorescence, measured the cosmic ray spectrum out to beyond 10 to the 20th eV. One experiment saw that the spectrum just kept going, didn't cut off at all. And this is very hard to understand because the cosmic rays will eventually interact with a cosmic microwave background, which means that the atmosphere, even empty space, is viscous to these cosmic rays because they collide with the photon and may have enough energy to make secondary pions and hence lose energy. So this is very hard to understand. And the other experiment using the fluorescence technique showed a drop-off here, which is more likely as to what one would expect because of this effect with the microwave background. This is about 2004 when the large array in Argentina began to operate. Now, just to show the beauty of this one result, this is the spectrum now seen by the Auger Observatory. I mean, compared to what we had before with this. And you see several features. There's a flat part here. This is a logarithmic plot. It is the number of events versus energy, this being 10 to the 20th electron volts. And you see a feature here which is recognized and agreed on as the ankle. But then what we were able to show, this is one of a number of results, is that the spectrum dramatically falls off, so it drops by nearly a factor of 100 by the time you're a little bit above 10 to the 20th eV, which just simply shows that you have to build something big enough and sensitive enough and carefully enough designed so that you can make careful and accurate measurements. And now, the concluding slide, so what about space? Well, in about 2 weeks, the ultimate detector called the Alpha Magnetic Spectrometer is going to be launched and placed on the space station. Here is a detector. It's a magnetic spectrometer, permanent magnetic spectrometer with many, many different kinds of detectors in, which can measure the flux of the cosmic rays, can identify electrons, positrons, protons, alpha particles, and so forth. And it's going to be launched just in 2 weeks, very exciting, and it goes on the space station right here. And this is a very expensive piece of apparatus. I mean, the proponents claim it's $1 billion. Well, I think $1 billion went into developing it. Probably, the actual cost of this is somewhat less. But what it will do is it'll measure in great detail cosmic rays of lower energy, 10 to the 11th. And right now there are begging to be answered interesting problems concerned with dark matter, which provides 20% of the energy content of the universe. Antimatter, does it exist in the universe? That would be quite a shock. And this is done by measuring helium to antihelium, and probably get a limit on antihelium, and other exotic particles. It's a beautiful, beautiful detector and is employing the last shuttle launch. And Professor Ting, who's the leader of this, was able to go to the US Congress and get a bill passed to have one more shuttle flight for this. That's a chutzpah that just impresses me very much. I had once told him that, Sam, if you were doing Auger, you would have had it built both in the north and the south, and both running by now. So, dear audience, that's my talk.